So find the surface area by rotating the curve about the x-axis. So our curve is y equals x cubed, and we're doing it over this interval about the x-axis. And since I'm given x values, not that this will always be the case, I'm guessing probably this is going to be a dx problem, since I'm already given x values. Again, that's not always the case, because I could always use these x values, plug them in, and get y values and find limits of integration for a dy problem, but I'm thinking maybe I'll end up with a dx problem. So let's quickly look at the shape. I'm rotating y equals x cubed about the x-axis, so it's going to generate something like this. And I'm interested in the surface area of that piece. So since it's an x-axis rotation, I really don't have a choice but to start with 2 pi y ds. Because it's an x-axis rotation, I must have the 2 pi y business involved. Now I have to look at this guy and figure out if I want to set up a dx problem or a dy problem. So step 1 is done. It was 2 pi y ds. For my ds, again, since I'm given x values and y is already isolated, I'm going to be finding y prime because it's what f as a function of x. So for ds, I'm thinking I'm going to do 1 plus f prime of x squared dx that I'm dealing with. Again, this is a choice I made because y was already isolated, and I have my limits of integration ready to go as x values, so I might as well use this. So y prime is 3x squared. This is all arc length stuff that we did from before, and then y prime squared is going to be 9x to the 4th, and then I have 1 plus that thing, 1 plus 9x to the 4th dx. So I got my ds, I put it in, and then I'm ready to start doing the integral. So I got my 2 pi y ds that I found, and I know that's a dx problem. So from 0 to 2 were my limits of integration for x values. And remember, my third step was to adjust x and y as needed. And here's what I mean. You set up your integral, you're ready to go. However, this guy right here is causing an issue because you have a problem, an integral dealing only with x's, but you have a y there that's annoying you. Well, that's not a big deal because you know to replace that y with its equivalent x version. So adjust x and y as needed or accordingly simply means if the integral you set up is not all in terms of the same variable you were dealing with or wanted to deal with, adjust them. So I don't like the y there. I want everything in terms of x's, and I do know that y was equivalent to x cubed. So I'm just going to go and set up my integral as 0 to 2 pi, replace the y with x cubed, and now I have an integral that I can actually evaluate. Everything is in terms of x's. So let's go try evaluating this integral. I'm going to pull out the constant 2 pi, 0 to 2 x cubed, 1 plus 9x to the 4th dx. And even though it looks ugly and complicated, things might be okay because it looks like it's a simple u sub. If I let u be this guy under the radical, it looks like my du will pick up this x cubed that's sitting here. So let's go do a quick u sub. So I got my 2 pi outside. I got this taken care of as a square root of u. And then this guy and this guy got picked up by my du over 36. So I'll put the du here and the 1 over 36 outside. And let's go ahead and change our limits of integration so that we don't have to worry about coming back into x's and can just deal with u's. So when x is 0 here, this piece is gone and u happens to be just 1. And when x is 2 and I put 2 in here, 2 to the 4th is 16 times 9 plus 1, that's 144, plus 1, 145. So I changed my limits of integration. Now I'm ready to go do this integral that's not so bad at all. So we got pi over 18, u to the half, that's going to go to u to the 3/2 over 2/3, evaluated from 1 to 145. So for an exact answer, we got pi over 27, quantity 145 to the 3/2 minus 1, if an exact answer is required, or punch that into your calculator and you get approximately 2 or 3 square units. Whatever units we're dealing with, remember this is surface area, so we're dealing with units squared. So 2 or 3 approximately units squared, whatever material is needed to cover the outside of this shape, basically. Now, since these guys are some busy problems, it might be a good idea, once you get your answer, to see if roughly you did the integration okay. Remember, you always have access to your TI. So let's go quickly put that in there. So I'm going to go to Math 9 and then input this integrand from 0 to 2. So we got x cubed square root of 1 plus 9x to the 4th in terms of x from 0 to 2. And I'm going to push enter. And then I got to multiply that guy by 2 pi, which I had pulled outside, times 2 pi. And I do get the approximately 2 or 3 square units that I had obtained by punching this business into my calculator. So it looks like everything looks good and I can move on. Let's look at another example. It says find the surface area, rotate about the x-axis again, and this is the shape from 1 to 2 in y values. So again, I'm kind of thinking maybe it's going to be a dy problem because y values are given to me, but not necessarily, but I'm sort of leaning that way. Well, this shape happens to be a sideways parabola, and I guess we're only concerned with the top half because y's are between 1 and 2. So it's a sideways parabola going like this, with the vertex it looks like at 1, 0. But we're only interested in the y values from 1 to 2, so this piece is only what we're looking at, and we're doing, it looks like, an x-axis rotation. So the shape we're interested in is something like that, I guess. We want to know how much is needed to cover that shape. So since it's at about the x-axis, I don't have a choice. The surface area will be 2 pi y ds that I'm dealing with. That's my first step. Step 2, I have to find my ds and see which version I want to deal with. And since x is isolated, it does look like I'm going to have a dy problem. So let's go find dx dy. So I'm using this version of my ds. Since the x is already isolated, and I will have a dy problem. X prime is just going to be, that guy's going to go to 0, bring down the 2 for y. Let's square that guy, and we get 16y squared when we square it. And so our ds piece will just be 1 plus that guy, dy. So we can go to our integral. It's going to be 2 pi y, and here is my ds piece. 1 plus 16y squared dy. I was interested from 1 to 2. And step 3 is not needed here. Notice you do not need to adjust x and y because everything is already in terms of y. You don't need to go back and mess around with this y. So your integral is all ready to go and ready to be integrated. So let's go try to integrate this thing. And again, even though square roots and business involved, it doesn't look that bad at all because it looks like it's a u sub. If I let this be my u, my du will pop or pick up that y that's lingering around. So it looks like I have 2 pi. This piece was just square root of u, and then this piece and this piece got picked up with the du over 32. So du, and I'll put 1 over 32 outside. Let's go ahead and change our limits of integration. If y is 1, that's just going to be 16 plus 1, which is 17. And if y is 2, that's just going to be 4 times 16, 64, plus another 1 is going to be 65. So just another square root integral to deal with. So the rest of the problem is not so bad. We have u to the half, that's u to the 3/2, 2/3. Simplify a little from 17 to 65. And as an exact answer, that's what we're going to get. If we punch that into our calculator, we get about 59 square units, if we can do approximations. And again, you can check this by also, instead of plugging this into your calculator, just going directly and doing an integral on your TI to make sure you didn't go anywhere wrong in the integration. Let's look at one more example in this video. Okay, the curve here is rotated about the y-axis this time. Find the resulting surface area. So it looks like we're looking at an upside down parabola, and only its right half between 0 and 1 rotated about the y-axis this time. So I got an upside down parabola, and we're only interested in the region from 0 to 1 on this side, and we're rotating it about the y-axis. So when we rotate this, we get this side, and so we're looking at the surface area of that piece. So since it's a y-axis rotation, I don't have a choice. S will be 2 pi x ds because it's a y-axis rotation. So at the beginning, I don't have a choice. I have to do that. Now, for my ds part, I'm given x values, so I'm leaning towards a dx problem for my ds analysis. And also, since y is isolated, that seems to be the way to go, because when I find y prime, everything will be in terms of x's. So I'm going to be using this version of my ds. Y prime is going to be constant goes to 0, bring down the 2, negative 2x. Let's square that guy. When we square it, we get 4x squared. And then finally, our ds will be 1 plus that business, dx. So we're ready to set up our integral. 2 pi x ds, which we used from here. And since it's a dx problem, my limits of integration are already given to me from 0 to 1. And again, step 3, there's no need to adjust anything because everything is already in terms of x's, and I'm ready to go and integrate. And it looks a whole lot like the other ones. It seems to be a simple u step, so we'll go through that quickly. So u is going to be what I got there. I have my 2 pi. This got picked up with the square root of u. And this guy are just du over 8. I'll put the 1 over 8 outside. Let's change our limits of integration. When x is 0, this is gone and u is 1. When x is 1, it looks like I get a 5 for my upper limit. A simple integral, u to the half, so u to the 3 halves 2/3 from 1 to 5. And it looks like we got pi over 6, quantity 5 to the 3 halves minus 1. And if needed to be approximated, approximately 5.33 square units is required to cover that shape. And again, as a double check, you might want to go into your TI and put that in from the beginning to make sure you get that. In the next video, we will look at a problem where we choose to set it up 2 different ways. Whether we do a dy problem or a dx problem, again, doesn't matter. Sometimes one ends up being easier than the other. So in the next video, let's set one up 2 different ways.